I am Andrew Medina, and for today I'll give you a video lecture on how I came up with my answers for the relative velocity assignment using graphical methods. Okay, so the item that I chose to solve was question 1, and we are given these measurements, and we're also given this mechanism. Now, I covered how to draw this exact mechanism in my previous video, labeled displacement analysis, and we are tasked to solve for the velocity of E when we are given the angular speed at which the crank turns counterclockwise in RPM, or revolutions per minute. So before we do anything, let us measure the parts of our mechanism and see if our drawing is correct. Now we use a scale of 10 centimeters to 1. So what that basically means is every 10 centimeters from the given would be equal to 1 centimeter on our ruler. So let us check. This would be 3.5, 35 centimeters, correct? This would be 4.5, 45 centimeters. This would be another 45 centimeters. 4.5, correct? And this would be 40 centimeters. Okay, correct? So in order to find the instantaneous velocity at E, we have to first find the velocity at C, and then we'll move forward until we reach the instantaneous velocity at E. So the first thing we have to do, first things first, is to find the velocity at C. Now let us remember that there's a formula for this, okay, in which we multiply the measurement of A to C, and we multiply it by the angular speed at which the crank rotates, which is given in 100 rotations per minute. Now the important thing to note is we must use radians per second if we're going to use centimeters, because we want to have an answer in centimeters per second, right? That's what's being asked. So we have to convert this 100 rotations per minute into radians per second. And let us remember the conversion is 1 RPM is equal to 0.10472 radians per second. Okay? So putting that into our calculator, we have 100 multiplied by 0.10472. And we will have the answer as the angular speed at A would be 10.4472 radians per second. Okay, so solving for the velocity at C, we're going to multiply this by the measurement from A to C, the measurement of our crank. So let us multiply that. And this would be the velocity at C. In centimeters per second. This is a very important and key point in solving for the instantaneous velocity at E. The reason why we want to find the velocity of C first in order to find the instantaneous velocity at E is because the velocity at C is the only velocity value that we can find using this formula. Okay, the rest of the velocities in this mechanism at the different joints must be found either through graphical method or another method. But for today, we're going to use graphical method. So in order to find the instantaneous velocity at E, we must know first the instantaneous velocity, the velocity at D, and we also need to know the velocity at c. So now that we have the numerical value for the velocity at c, we need to convert that into a line that we will use. So first things first, we're gonna make a line that is perpendicular to c, AC, and then we're gonna capture that angle and project it here, and then we're gonna redraw this as a line, this numerical value as a line. So let us do that. Now that we have our perpendicular line from AC, we can measure this, and I measured it as around 30 degrees, which makes sense because 30 plus 90 plus 60 would equal 180 from our origin line. So this makes perfect sense. And we turn this value, 366.52 centimeters, into a line from here to here. And this would represent our velocity at c. Now this scale, we copied the angular measurement here. We used 1:1/2 scale to be more accurate, because if we were to use the 10:1, then it would be highly inaccurate. And what we got from our calculator, dividing it by 2, is 183.26 centimeters. And that's what we have here. 183, roughly. Now next we need to do is draw lines perpendicular from BD and perpendicular from CD. This would represent, I'll show you in a minute. This line would represent the velocity of D, and this perpendicular line would represent the velocity of D in respect to C. So let us just project those lines onto our point of origin with the exact measurement of the degree from an origin line here, exactly similar to this, to get the angular measurement of how long our lines need to be. Okay, so this is actually pretty straightforward. After getting the perpendicular lines from these particular segments, we now have to measure their angle from a point of origin or origin line. So I measured this at 12 degrees and I measured this as 72 degrees. And now we input these into our graphical method figure. Okay, so we're gonna have the velocity of D from the origin, and then from velocity of C, we're gonna draw straight from here the velocity of D with respect to joint C. The velocity of D in respect to C. So we just copy these angles, 12 degrees and 72 degrees, and we project it straight onto this figure. And then we would measure where this would intersect, and we would have here the velocity of D. And if we measure it, we would have around roughly 124 centimeters, roughly. And now let's remember our 1:1/2 scale. We'll multiply 124 or 123.9 times 2. We would have the velocity of D would equal 247.8 centimeters per second. Okay, so this is a very important number, and we will use this to find the instantaneous value or the instantaneous velocity at E. Very simply, what we have to do next is to copy exactly the graphical representation of the velocity at D in order to find the instantaneous value of the velocity at E. And we're going to use this. We're going to use the velocity at D to make a similar figure to this, to find the velocity at E and the velocity at E with respect to D. So what we did, we copied exactly this here, where we have roughly 12 degrees, and we have our value VD, but we remember the scale is 1:1/2. So now what we have to do is to measure the degree or the angle of VED with respect to a specific line of origin and project it here and have it intersect, hopefully, with the velocity of E, which is projected from the point of origin here. So let us do that now. Now that we've copied exactly the angles present within the given mechanism and projected them successfully, we can now do the final step in finding the velocity of E, instantaneous velocity of E in the mechanism. Now we find where it intersects and then we measure it, and it's around 104.3. And remember our scale, 1:1/2. So 104.3 times 2 would give us 208.6. So the final answer would be 208.6 centimeters per second. Thank you.